Hi, welcome to one and all. Next, we will be discussing one more problem on quadratic residues. That is, find the quadratic residues modulo 17 and the quadratic non-residues modulo 17. This is in continuation to the problem of quadratic residues mod 11. So let us see how to find the quadratic residues. That as earlier we have seen, we have to find the squares of the numbers which are less than 17 and then divide those numbers squares by 17 and take the remainders. That numbers will be the quadratic residues. So here we could see that we need only find 8 numbers. That is, we don't want to find all the squares of all the numbers. We just take half of the numbers of this. That is, if this is p, 17 is p, then p minus 1 by 2 numbers we have to take. That is, p minus 1 is 17, minus 1 is 16, 16 by 2 is 8. So 8 numbers we have to find the squares of the first 8 numbers. Then that the remainders will be repeating again. So let us see. So x is 1, 2, 3, 4, etc. up to 8. Squares, if you take, it is 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16. So remainder is up to that, the remainders are the same, and 5 square is 25, so remainder is 8, 6 square is 36, remainder is 2, 7 square is 49, so remainder is 15, and 8 square is 64, the remainder is 13. Then 9 square will be 13. 7 square and 10 square will be as same as 7 square, that is 15. Like that it will go in the reverse order. That is, if this is k, then the remaining numbers, that is p minus k, are is nothing but that will be the remainders in this order. So you could see that 1 square is 1, 2 square is 4, 1 square is converted to 1 mod 17, 2 square is converted to 4 mod 17, 3 square is converted to 9 mod 17, 4 square is converted to 16 mod 17, which is sorry, it is typing mistake. Here it is 16, 4 square is 16, this is wrong, and 5 square is 25, so 8 will be the remainder. 6 square is 36, so 2 will be the remainder, because 34 is 2 times 17, 34, so remainder is 2. 7 square is 49, so 15. 8 square is 64, so remainder is 13. So like that. So this will be the numbers we are going to we will get. That is, the quadratic residues will be 1 and sorry, 2 is here. Yeah, 2 is also there, so 2 is there, then 4 is there, then 8 is there, then 9 is there, then 13 is there, then 15 is there. So 1 are 17, 2 are 17, 4 are 17, 8 are 17, 9 are 17, 13 are 17, 15 are 17, 16 are 17. So these are the numbers. The quadratic non-residues are 5, 3, 5, 6, 7, 10, 11, 12, 14. We write 3 r bar 17, 5 r bar 17, 6 r bar 17, like that. So now let us see one of the consequence of this problem. That is, let P be a odd prime, then every reduced residue system mode P contains exactly P minus 1 by 2 quadratic residues and exactly P minus 1 by 2 non-quadratic non-residues mode P. This is what we have to prove. The quadratic residues belong to the residue classes containing the numbers 1 square, 2 square, 3 square, etc. P minus 1 by 2 the whole square. So this is what we have to prove. So proof is quite simple. We could see that first we show that the numbers in 2 are distinct mode P. That is, we have to show that each of the remainders which we are getting is distinct. For that, suppose that they are not distinct, then clearly some of the numbers will be same. They are not distinct means they are some are same. So that is, x square is congruent to y square mod P, where x is nothing but a number between these, that is 1 and P minus 1 by 2, and y is also a number between 1 and P minus 1 by 2. So clearly x square is constant to y square, so we can take this y square to this side. So x square minus y square is constant to 0 mod p, with 1 less than or equal x less than or equal p minus 1 by 2 and 1 less than or equal y less than or equal p minus 1 by 2. Then clearly we can take this x square minus y square is x minus y into x plus y, which is constant to 0 mod p. So this means that p divides x minus y times x plus y. So we could see here that p should either divide x minus y or p should divide x plus y. Now let us take the case of x plus y. When you divide these two, see 1 and 1, 2, x and y you add, that is 1 plus 1 is 2, x and y you add x plus y, and this is p minus 1 by 2 plus p minus 1 by 2, it is p. So you could see that p minus 1 by 2, p minus 1 by 2 will be p minus 1, and p minus 1, so here it should be p minus 1. So you could see that 2 less than or equal to x plus y less than or equal to p minus 1. So clearly 2 is less than 1, so 2 is less than 1, which is less than x plus y, which is less than p minus 1, and which is less than p, because p minus 1 is less than p. P minus 1 is great, p is greater than p minus 1. So clearly 1 is less than x plus y less than p. Hence p does not divide x plus y, because it is a number which is less than. So p does not divide x plus y. Then clearly p should divide x minus y. So therefore p divides x minus y. What is the meaning of that? It means that x minus y is constant to 0 mod p. What is the meaning of that? This x is constant to y mod p. Which means that numbers in 2 are distinct mod p. That means this is not possible. X is equal to y. So x is equal to y means both are same. If we are taking distinct, it is same. So hence x and y are same. So that means the all numbers are distinct here. Now in the example we have seen that we need only to take the numbers half the numbers, that is from 1 to 8. No need to take from 9 to 16. So that is what, if you take one number as k, then the other number will be minus k, which is p minus k. We call it as minus k because the numbers are in the reverse order, remainders are in the reverse order, so they have the same squares mod p. So we can say that p minus k the whole square is constant to k square mod p. Hence every quadratic residue is constant mod p to exactly one of the numbers in 2. So this completes the proof. I hope you have understood. There is one correction here, that is 2 is p minus 1, so that it will be p. Anyhow this is also correct, but here as we add these two it will be p minus 1, so that you have to record. Hope you understood this concept. Now let us quickly look the examples. Following table gives the quadratic residues R and non-residues R bar where by using this theorem. So only half the numbers we have to see. So R, P is equal to 3, P equal to 5, P equal to 7, P equal to 11, and P equal to 13. The numbers are given. R is 1, only 1. P equal to 5, it is 1 and 4. P equal to 7, we have 1, 2, and 4. They are quadratic residues. For P equal to 11, 1, 3, 4, 5, and 9, that we have seen already. P equal to 13, 1, 3, 4, 9, 10, 17, 12. So for non-residues are 2. Here P equal to 5, it is 2 and 3. P equal to 7, it is 3, 5, and 6. And P equal to 11, it is 2, 6, 7, 8, and 10. P equal to 13, it is 2, 5, 6, 7, 8, and 11. So I hope this is not a difficult thing to construct the problem or find the quadratic residues modulo P and the quadratic non-residues modulo P. Hope you have understood the concept properly. Thank you very much. Thank you for your patient listening. Thank you.